In this chapter, we're going to learn dimension reduction. So dimension reduction is one of unsupervised learning task. So without the label, we can reduce the dimensionality of the data set. Okay, and in this chapter, we're going to learn why we need this dimension reduction and what kind of algorithms we have. So first, we'll talk about dimension reduction, and then there are many dimension reduction algorithms, but in this chapter, we're going to cover just linear algorithms, okay, PCA and FA, MDS, LDA, and ICA, NMF. And the nonlinear dimension reduction algorithms will be covered in the next chapter. Okay, what is dimension reduction? So basically, in general, if we have more features, then they provide more information. They include a lot of information there, and potentially they provide high accuracy for a task. Okay, that's good. This is positive thing, but there's no free lunch and there is a cost. So if we have more features, then it's harder to train a classifier because the classifier has more parameters. Okay, and then if we have more parameters, then we need more data samples. So that can be summarized by the curse of dimensionality. So this one says that if we increase the dimensionality by 1, then we need exponentially more training samples. Okay. So if we increase the dimensionality by a few numbers, then we need a lot of more data samples to train the classifier. Okay, that is the curse of dimensionality. And also, more features could increase possibility of overfitting. So basically, these two things says the same thing. Okay. Actually, it is the other side of the same coin. Okay, in this case, if we increase the dimensionality, then we need exponentially more data samples. But that's not the case. Usually we don't have that many data samples. Then what happens? If we don't have enough samples to train the classifier, then we have overfitting. Okay, so basically these two things say the same thing. And about this overfitting, don't worry, we will talk about this thing in detail in the in regression. Okay, in the regression chapter. Okay, and so in that case, so we have a lot of features, but we don't have many samples. Then this is a problem. In this case, dimensionality reduction algorithms come to the rescue, like PCR, principal component regression. Okay, so they don't use all the features as a factor. Okay, so they reduce the dimension first. So let's say we have 100 features. Okay, 1,000 features, and that is too many features. Then we reduce the dimensionality from 1,000 to say 10. Okay, then we're gonna build a classifier, or we're gonna build some machine learning algorithm based on this 10-dimensional space. Okay, instead of 1,000-dimensional space. That's what dimension reduction does, and it finds continuous latent variables. Continuous latent variable means this 10-dimensional space in this example. So we have a 1,000 dimensional space. This one is the space where our data samples exist. Observable space. And this space is not observable, it's hidden, it's latent. So in the clustering algorithms, we actually assigned all the samples into categories. Okay, so let's say 1,000, this is dimensions. Let's say we have 2,000 samples, and we assigned 2,000 samples into 3 categories, which means one cluster, this one will generate the sum of these samples, and this one generates some of this, and this one will generate some of this. So these are kind of discrete latent variables. But this one is 10-dimensional space. From 10-dimensional space, we have a vector, and this vector is corresponding to one data sample in the 1000 dimensional space. So 200 samples will be transformed into this 10-dimensional space. So in 1000 dimensional space, we have 2000 samples. In 10-dimensional space, we have 2000 samples. So dimension reduction is finding continuous latent variables, and the clustering finds discrete latent variables. Okay, and for example, we have an image like this. Then each image has 20 by 20 pixels, 400 pixels, which means one image is a point in 400 dimensional space, which is quite high dimensional space. Okay, but think about this one. When face images are generated with three latent variables, okay, left, right pose, and up, down pose, and light directions. So if we have only three factors, which is three latent variables, with these three factors, okay, we actually change the image. Okay, so if we take a photo, face photo, okay, if we change the light, the pose, and if we change up down pose, and if we change the light direction, then we might have lots of images, face images. But think about this one. All these images are actually the same image in the different pose and with different lighting direction. Then we can see these three-dimensional factors. Okay, so based on these three-dimensional factors, we actually generated a lot of face images. Okay, and this is what I just said. Faces lie on a three-dimensional manifold embedded in the 400-dimensional image space. Okay. As I said, images can be generated by translation, up, down, left, right, and rotation. So the same image 3 can be rotated and translated to generate lots of images. But in this case, if you look at these pixels, this image might be too easy, but in general, think about some face image with some background. Okay, then if we translate and if we rotate the face, then we generate lots of face images. But if you look at the pixels, if you look at the face images pixel by pixel, then this image and this image is completely different. In this case, yes, backgrounds have the same pixels, but in general, lots of pixels will have different intensity. Okay, they change. So even in this case, let's say if it is 20 by 20 images, then probably around 100 pixels might change with these operators. But even when the 100 pixels are changing, but actually we just apply three operators. So we have only three factors. So dimension reduction is actually interested in these factors, hidden variables. This is continuous latent variables. Okay. And the PCA, or principal component analysis, is one of the most popular and the simplest dimension reduction methods, and it is a linear projection, and it finds an orthogonal basis set that makes the largest possible variance on the linearly projected space. So this figure explains pretty much of a PCA. So we have a lot of data samples as a blue dots, and then this one, think about this one. If we have to use just one dimension to represent all these data samples, then which dimension would be the best? So this one. It's the best dimensions. And what is the next? This one is the second. If we have a three-dimensional space, then we have first dimension and the second dimension and the third dimension. So basically, we want to preserve all the information of these samples. So in this case, if we represent all these data samples with one-dimensional space, then these samples should be projected onto this axis. Then each data point lose some information, this much. Okay, but this one will lose a little of information, but this one will lose lots of information. But think about this one. If we have a dimension in these directions, then this one will lose a lot of information. This one will lose lots of information, lots of information. Yes, these ones will not lose a lot of information, but we have many data samples who are losing lots of information when they are projected onto this dimensional space. So this dimension is better than this one. Intuitively, you can understand that, right? So we're going to prove that. We're going to prove why this direction is the best direction with some equations. Okay, first, PCA minimizes reconstruction error. Reconstruction, what is the reconstruction? So in this figure, we have a three-dimensional space. Okay, and then we want to project. For now, you don't have to understand what kind of W we have. Okay, so for now, let's assume that we have a two-dimensional vector, and we're going to project all the data samples with the two vectors. So now we have a two-dimensional representation like this. So we just project it, and then after projecting, then we can reconstruct these three-dimensional vectors, three-dimensional samples from the two-dimensional space. So when we actually reconstruct, then we lose this much information. If we have a sample right on this two-dimensional space in this three-dimensional space, if we have a sample on this kind of paper, then when we project and then when we reconstruct, there's no reconstruction error. It's perfect. But if we have a sample like this, then when we project, then this sample would be on this two-dimensional space as a one point. Then when we reconstruct, then this one will be around here. Okay, so we cannot go up actually. We lost that information. So PCA want to minimize this error. So when we reconstruct the data samples after projections, then the PCA wants to minimize this error. So it minimizes reconstruction error. Okay, the question is how? Okay. And also at the same time, PCA maximizes preserved variance after projection. So in this slide, we are going to prove that this minimal reconstruction error from the previous slide is the same as maximal preserved variance. So preserved variance means after projections. After projection, we can calculate the variance. And that variance should be maximized if it is a PCA. Okay. So let's see how these two are the same. So given a centered data matrix, the centered data matrix means when we actually calculate the average of these data samples, the average is origin, is a zero vector. Okay, so we can do that. And many times we do this, or sometimes we assume this. Okay, and when we have a centered data matrix X, then RSS, the reconstruction error, can be represented by this. Okay, so if you look at this figure, then you can understand why this is an error. So this one is original vector, okay, and this one is a projected vector. Actually, If W is vector, then this one is a scalar. So we are projecting the data samples into one-dimensional space. So we are talking about just one-dimensional space here. Okay, and this is a projection, and then this one is actually a reconstruction. So we project x sub I onto this vector, and then we reconstruct this scalar with the vector w into the original space. So this one is a reconstructed vector, so that's why this is a reconstructed error. And obviously, the norm of w should be 1. Otherwise, when we project and reconstruct, we have to multiply constant and divide the number with the constant, so it's complicated. So for convenience, then we just put this constraint. Okay, then when we rewrite this reconstruction error, then we get this term. So it's a simple derivation. And then argmin with respect to w is of this reconstruction error is equivalent to argmax of this one, because this one is fixed. It is not changing when we change w, so it is constant. Okay, when it comes to w, with respect to w, this is constant. So by changing w, we can actually change this part. So argmax w RSS is exactly the same as argmax w this term. Okay, and then when we derive this variance of this one means actually preserved variance. After projection, what is the variance? Okay, so when we actually calculate this variance after projection, then we get this one. This one is just the definition of a variance. And look at this one. This one is actually 1 over n w xi transpose n square, because w is kind of constant, so we can actually put this w out of this summation. And look at this one. We assume that the data is already centered, so this one is 0, so it just cancel. And now variance is this one, and this one is exactly the same as this term. So now we just proved this one. Minimal reconstruction error is exactly the same as maximal preserved variance. Okay, so this one says, when we project our data samples onto one vector, then we want to minimize this error. After projection, we want to minimize this error. Or this one is exactly the same as we want to maximize the preserved variance. So if we project the samples here, then look at these samples on this vector. The variance is high. But if we project the samples onto this vector, okay, then we'll have lots of samples like this, and the variance is quite small. So this one is the vector with the maximal preserved variance. So these two things are basically the same things. We just proved with the equation. Okay, now on this slide, so we're gonna drive this maximal preserved variance to eigendecomposition problem. So it says finding the maximal preserved variance is finding the eigenvalue, the largest eigenvalue and eigenvector. Okay, so this variance can be rewritten like this. Instead of using summation, then we have a matrix notation here. So X is actually set of all the data samples. And then we can rewrite this equation like this. And finding the argmax W of this variance with this constraint can be done by Lagrangian multiply, Lagrangian function. So this one is Lagrangian function with Lagrangian multiply here. So this one is actually this one. And if we put C like this, okay, then 1 over n and x transpose is C. So which means this one is W transpose CW. Okay, so we have objective function to maximize, and we have a constraint. So now we are going to use a Lagrangian function. Okay, and this one is here, and this one is a constraint, so we put the Lagrangian multiplier and we have a constraint here. Okay, then next step is to take a derivative with respect to W. Okay, so this one is here and this one goes here. And then we got this one. CW is lambda W. This is exactly eigendecomposition problem. Okay, so W and lambda are the eigenvector and eigenvalue of covariance matrix C. Okay, so maximal preserved variance is exactly the same as the largest eigenvalue. And when we have maximum preserved variance, the vector W is actually the largest eigenvector. Okay, so we can rewrite this problem with this objective function. Okay, and this one is a Rayleigh quotient. So in general, Rayleigh quotient can be defined by this ratio. Okay, so we have one matrix here and another matrix here. But in the previous slide, S was identity matrix. It's a special case of a Rayleigh quotient. But in general, we have this term. Okay, so to solve this problem, to maximize this Rayleigh quotient with respect to W, this maximization problem is exactly the same as this Lagrangian problem. Okay, and look at this one. We can derive this term again in general. So considering the scale invariance like this, JCW, C is constant, we multiply constant to a W vector, then we have a C here and the C and C and the C here. Okay, then this C can go out, so we have a C square and C square here. Okay, then we can cancel these each other. And then this one is exactly the same as JW. So if we multiply some constant to W, it is exactly the same as original objective function. So it is sufficient to consider that W transpose SW is 1. Okay, because it doesn't matter. There is an invariance here. So we use this one as a constraint. Then we multiply Lagrangian multiplier to make a Lagrangian function here. So this one and this one is exactly the same. Okay, same problem. So let's solve this problem in general. So when the S is invertible, in the previous slide the S was identity matrix, which is invertible. So the previous slide corresponds to this case 1. Okay, when we when we take derivative of this, then we get this one. And we have this equation. And if S is invertible, then we have this problem, this equation. And this one is one matrix. And this one is exactly eigendecomposition problem. Okay, one matrix, W is lambda W. Okay. But if S is not invertible, then we have to add another constraint, this one. So we had one constraint, and we won't have another constraint. And then from this, we have a first Lagrange multiplier and second Lagrange multiplier. And we take a derivative with respect to W, then we have this term, okay. Then finally, we have this equation. So in this case, beta I is actually a regularization because S is not invertible. So we have some identity matrix times some constant. So look at this equation, the matrix. This matrix is not invertible with some values. And then if it is not invertible, then if we add some strong value on the diagonal element, then it will become invertible. So if we increase beta, then at some point this one will be invertible. So we can take an inverse of this matrix. Now we can solve this problem. So this slide is kind of a little extra, but this slide shows that this one is actually a generalized eigenvalue decomposition problem, which is exactly the same as this one. And this one shows us the solution of solution of principal component analysis. Now let's take some examples. And the first five eigenvectors of covariance matrix of MNIST data samples look like this. Again, the one MNIST data sample, the size of the data sample is 28 by 28 matrix. Okay, but when we consider data samples, then we just use a vector. Okay, and 28 by 28 times 1 dimensional vector. Okay, so after eigendecomposition, then eigenvectors will be a vector in the 28 by 28 dimensional space. Okay, this is one eigenvector. Then we can reshape to make a image, and this one is corresponding to this one, and this one, and this one. So we actually show the 5 eigenvectors, and actually we have 28 by 28 eigenvectors. Okay, and when we plot the eigenvalues, then we can have this curve, and based on this, then we can calculate the eigenvalue ratio R sub k. Then we sum the first k eigenvalues here, and then over all the sum of all the eigenvalues. Okay, and that is eigenvalue ratio. And if we use 10 eigenvalues, so it means k is 10, then it is 48.9%, which means if we use first 10 dimensional space, then we can represent almost the half of the variance. Okay, and if we use 50, then it can cover 82.5%. And if we use 100 eigendimensional space, then we can cover 91.5%. So instead of using 28 times 28 dimensional vector, if we use just 100 dimensional space, then we can represent 91.5% of all the information. Okay, so we can use this kind of principle for data compression or pre-processing or feature extractor. So we can actually extract some features in low-dimensional space, or we can use it for data visualizations. For data visualization, we need to project the data into two-dimensional space or at most three-dimensional space. Okay, so if we have four-dimensional vectors, then it's not possible to visualize. Okay, so we can use this for many applications. And especially if we apply eigendecomposition to face data, then we can have these face images as an eigen vectors. This one image corresponds to one eigenvector, so we call it eigenface. Okay, so given this data set, and we can get these eigen faces. So look at this one. The first eigenface represents the most common face. Okay, and the last one will focus on just not frequent features.